Hello students, welcome to this 20th lecture session of the course Database Management Systems. In the previous session, that is in lecture session 19, we clearly understood what are the various steps involved in executing an SQL query. When an SQL query is submitted to the query engine of a database management system, first scanning is done with an intention to create or generate tokens of the SQL language. Once tokenization is done, parsing will be carried out to check the syntactical correctness of the query. Once it is done, validation is done, where check for identifying the valid relation names and the attribute names that appear in the query will be conducted. Once it is done, then the query is divided into query blocks, and for each query block a appropriate corresponding relational algebraic expression is generated. Then the parser will represent the query block in an intermediate format, more likely in the form of a query tree. We understand that there can be many strategies possible to execute an SQL query, and it is the job of query optimizer to identify the most reasonable execution strategy which will be more efficient or effective. This we call it as query optimization. Then after this query optimization, after identifying the more reasonable effective strategy, then the code is generated where the query can be executed. Now in this session, that is lecture session 20, let us focus on the query optimization part. Here we discuss what is a query tree and what is a query graph, what are the various heuristic rules that are used in query optimization by an SQL query optimizer, and what are the various cost components using which we can estimate the cost of execution of an SQL query. Query optimization is the process of choosing a suitable strategy from the available set of strategies for the given SQL query. In this process, first an SQL query is translated into an equivalent relational algebra expression. Then it is represented as a query tree data structure. This query tree, which is an intermediate form or representation, is more suitable or amenable for optimization. That is, the query optimizer module is going to work on this intermediate form to optimize the query. A query tree is a tree data structure that corresponds to a relational algebraic expression. That means every relational algebraic expression can be represented as a query tree. Tree means it contains root, internal nodes, and then leaf nodes. And the tree represents the input relations of the query as leaf nodes. That is, whatever input relations are part of the query or relational algebraic expression, they appear as leaf nodes of the tree, and the tree represents the relational algebra operations like select, project, join, all these things as internal nodes. And even there can be an operation in the root node as well. The execution of the query starts in this query tree, and it starts from the leaf nodes, and internal node is executed when the corresponding operands are available. That means the query execution is starting at the leaf node and it proceeds upward direction. Whenever the operands are available for an internal node, that is, we understood that each internal node is nothing but an algebraic operation like select, projection, whatever it is. So when the operands are available to execute that operator, automatically it is executed and the temporary results is generated. That is, the intermediate result is generated, which is result of applying that algebraic operation. And it will proceed to the next level, because when an operation is executed, on the operands, the result is available Now that internal node is replaced with the result. Then we are ready to execute the operation which is available in the next higher level. The execution proceeds like this, and then when we execute the algebraic operation available at the root node, then we get the final result for the query. The execution terminates when the root node is executed and produces the result, a relation for the query. We understand that for any SQL operation or the relational algebraic expression, when we execute that, the result is also a relation. Okay, this is how the query tree works. That means the execution starts from the bottom, wherein at the bottom level, that is at the leaf level, we have only the relations that are involved in the expression. And the internal nodes and the root node, they are nothing but the algebra operators, relational algebraic operations. Let us have a look at this example. Here, select F name and salary from employee and department relations, where the condition is D name is equals to accounts and DNO is equals to D number. That is, this is the join condition between the employee table and the department table. I want to get the first name and salary of those employees who are working with accounts department. Department and employee table are different, and the department name is available in the department table, and the DNO is a foreign key in employee table, which forms the basis for joining the tuples in employee table and department table based on the condition DNO in employee table is same as the D number, which is the primary key of the department table. And there is no nested query available. Hence, this query can be treated as one single query block, and next immediately the corresponding relational algebraic expression is generated. I take the department table, I select only the tuples where D name is equals to accounts, then I join those tuples from department table where the department name is accounts with the tuples of the employee table. The join condition is where DNO in employee is equal to the D number in department table. From this result, that is when I execute this, you get a joined table. From this, I project on the first name and the salary. That is the result of this expression. And when this algebraic expression is given, automatically it is represented in the form of a query tree. The initial query tree that is generated by the system looks like this, where at the leaf level we have the relations that are involved in the expression. D stands for department. For the sake of brevity, the department table is represented as D and employee table is represented as E. And the very basic operation performed on this is the Cartesian product operation, where every tuple in department is joined with every tuple in the employee table. From that, I pick up only those tuples where DNO value is same as D number value. DNO is attribute of D and then DNO is attribute of E and then D number is attribute of D. Then I pick up only those tuples where the D name is equals to accounts. Then I project on F name and salary. This is known as the initial query tree. And another representation that is possible, intermediate representation for algebraic expression, is in the form of a graph, which we call it as a query graph. Relations in the query are represented by relation nodes, which are displayed as single circles like this, single circles. And I can write the relation name in the circle. And constant values typically from the query selection conditions are represented by constant nodes, and which are displayed as double circles with double borders, and then or the ovals, or they can be rounded rectangles. All these representations are valid for constant nodes. Selection and join conditions, or we can say that the operations, algebraic operations, are represented by the graph edges. That means the edges between the nodes represent the operations, algebraic operations like join, selection. Finally, the attributes to be retrieved from each relation are displayed in square brackets above each relation, exactly above the corresponding relation. query graphs will not indicate, the one drawback with these query graphs are they will not indicate the order in which the operations are to be executed. And that's why many of the optimizers, they need the order in which the operations need to be executed. Hence, query trees are more preferred to these query graphs. That is one important point to be noted. Let us have a look at the query graph for the given relational algebraic expression. Same relational algebra expression I have taken. Select F name, salary from employee, department, where D name is equals to accounts, and then DNO is equals to D number. And this is the corresponding relational algebraic expression. It is same as what we have seen in the case of the query tree. Now, I said that each relation is represented as a relation node. D is one relation node and then E is another relation node. And the constants which are used in select conditions are represented using the constant nodes, which here I have taken the representation. The notation is the rounded rectangles. And what is the constant I am using in select condition? Select those tuples from department table where D name is equals to accounts. Hence, the accounts is the constant and this constant node carries this label. Okay. Now, this select condition, the edges, this particular edge represents the select condition and this particular edge represents the join condition. Okay. This select condition is applicable to which relation? It is on department relation. I pick up the tuples from the department table based on this condition where D name is equals to accounts. And then I join the employee tuples and then department tuples after applying this selection condition on D name is equals to accounts, where the tuples will be joined based on the DNO is equals to D number. Of course, one drawback with this is you don't know whether this selection is applied first or join is applied first. Hence, the ordering of the operations, execution of these operations or sequencing of operations is not clear or not indicated in query graph. That is one drawback. You don't know whether this is first or this operation is first. Okay, nevertheless, once the tuples are joined and selection is done and finally it is to be projected, the result attributes are from the employee table, F name and salary. Hence, I am representing or giving this list of attributes that need to be shown in the result in square brackets and which is written exactly above the circle which represents the relation employee table, that is E. And this is known as the query graph, and it never indicates the sequencing or ordering of operations. That is one drawback. Hence, many optimizers, they use the query trees. They prefer query trees to these query graphs. And now let us see how the optimizer will apply heuristic rules to optimize the query trees. A query parser will generate a standard initial query tree, that what we have seen in the previous slide, and initially the initial standard query tree is generated and which is corresponding to the SQL query without doing any optimization. If these initial query trees are executed, they are not efficient. That means they are not effective. The performance wise, they may not be effective or efficient. Now, it is the job of the heuristic query optimizer to transform this initial query tree into a final query tree that is reasonably efficient. And of course, 100% optimization is not possible. These heuristic rules will help us in identifying a strategy where it is reasonably effective. The optimizer must include rules for equivalence among the relational algebra expressions that can be applied to initial tree. Heuristic query optimization rules then utilize these equivalence expressions to transform the initial tree into the final reasonably optimized query tree. Let us have a look at this example. And this is the query tree, initial query tree generated as a result of converting the relational algebraic expression which is given in the previous slides into initial query tree. D and E, then I apply Cartesian product, then I apply selection, and the joining of tuples will happen on DNO is equals to D number, finally projection. And if I execute this, it is not effective. And because I apply heuristic rules to minimize the cost or to minimize the size of the intermediate results or minimize the execution cost of operations. We already understood that the Cartesian product is a very costly operation, because if I take the Cartesian product of R and S, every tuple in R is joined with every tuple in S, and it takes a lot of time. At the same time, the size of the intermediate result is also very large. To avoid that, we will apply some heuristic rules. And not only that, in the intermediate result, if I can remove or eliminate the tuples which are not relevant with the operations or the result, then the size of the intermediate results can be reduced and the performance can be improved. If I want what from the department table, what kind of tuples I need in this query execution. I am concerned with only those tuples where the dname is equals to accounts. Hence, now what I will do is, whatever selection on this condition, that is dname is equals to accounts, I am performing after the Cartesian product operation. And when I optimize this, what I will do is, I will apply this selection condition on the department table before I perform the Cartesian product or join. If I have 10 tuples in department table, and if I know that there will be only one department with the name accounts, then why should I take all 10 tuples in Cartesian product or the join operation, which is costly. So it is a costly affair, because the cost and the size of the intermediate result will also be very large. To avoid that, what I can do is, first I can apply the selection condition on the department table, where I will pick up only those tuples that dname is equals to accounts, and I know that mostly I will get only one tuple from the department table. Okay, that I will use in Cartesian product or the next further subsequent operations. The next one more heuristic optimization I can perform is, why should I require all the attributes? If the department table has 12 attributes, why I need all the 12 attributes in further operations? It is not necessary. For the department tuple where the department name is accounts, I require only the department number, where I can use that to join with the tuples of employee table. Hence, immediately after selecting the department tuples based on dname is equals to accounts, I can perform the projection. I pick up only the department number. That is sufficient for me. I don't need all the attributes from the department table. That is not required. Okay. Now let us look at the employee table and then find out what optimizations I can apply. From the employee table, what attributes are required in the final result? Only the F name and salary are required. Okay, that's fine. And then what attributes are required to perform a join operation with the department tuples? I require the department number, and of course I can maintain the SSN, which is the unique key. And if the employee table contains 20 to 30 attributes, I don't have to consider all these 20 to 30 attributes while performing the subsequent join or Cartesian product operation. Hence, I will perform the projection operation on the employee table for these 4 attributes as early as possible. That means I am going to reduce the size of the relations I consider for the Cartesian product or the join operation. Okay. Yeah. Now let us look at the other possible optimizations. We already understood that the Cartesian product is a very costly operation. This join operation on some condition is same as Cartesian product of 2 relations and then applying some select condition. Hence, whenever there is a Cartesian product operation followed by some select condition, I can replace these two by one single join operation. Okay, that will reduce the costs. You see here, I am eliminating that Cartesian product operation, and where in the previous case there was a Cartesian product operation which is immediately followed by the selection operation for the tuples. Now I merge these two and then I use only one operation, that is the simple join, inner join operation. I join the tuples from this and this, where if I take the department table, I have only one tuple and I have only one attribute. And if I take employee table, maybe for all the tuples, I have only 4 attributes available. That means I have already minimized the size of the relations that I am considering for this join operation. Now I will perform the join operation based on the DNO from employee table is same as D number in department table. From this intermediate result, I will pick up only F name and salary into the final result. So this is the root of the query tree. When I execute the operator available at the root, then the final result of the query is available for the user. Okay, this is how the query optimization is done, and then an initial query tree can be optimized by replacing or changing the order of certain operations. Outlines of the heuristic optimization algorithm are as follows. That is the summary of heuristic rules. If the selection operation contains multiple selection conditions, we break up the conjunctive selection operation, which will help in moving the select operations down in different branches. Move each select operation as far down as possible in the query tree so that I can reduce the number of tuples I consider for the subsequent operations. Then more restrictive select conditions need to be executed first. What do you mean by more restrictive select condition? The select condition which will give me the minimal number of tuples from the operand relation is known as restrictive select condition. If I have 20 department tuples in the department table, and if I know that the department names are distinct, and then if I say that select the tuples from department where department name is equals to account, I know that there can be maximum only one tuple which is the result of that select operation. That is known as the more restrictive select condition. The rule says that apply more restrictive select conditions as early as possible. And the next rule is that combine the Cartesian product with a subsequent select in the tree into one single join operation if the condition represents a join. Okay, and that's what we have done in our example. That is, here a Cartesian product was there, immediately it was followed by some join condition which is the condition for the inner join. Then I replaced that with one simple single join operation. And similarly, the last rule says that break up project operations and move them as far down as possible in different branches. And if we apply these heuristic rules, then it is more likely that we will get a strategy which is reasonably effective and then efficient. Of course, we are not going to talk much about the query graphs because we understood that many query optimizers, they consider query trees more helpful or useful. And not only the heuristic rules, sometimes the optimizer will require to estimate the cost of execution of a query so that it can take a decision on deciding upon the more reasonably optimized or effective plan or strategy. So what are the cost components of query execution? That is, based on what I can compute the cost of a query. First factor is access cost to secondary storage. That is, this is the cost of searching for reading and then writing data blocks which are sitting on the disk. That is a very, very important and then dominant factor which decides upon the cost of an execution of a query. Okay, so how much time is required to search or access the blocks which are on the disk. Second cost component is the storage cost. Cost of storing intermediate files that are generated by executing the operations that are part of the query tree, which are available at the internal nodes. That is the size. Otherwise, it is directly proportional to the size of the intermediate result. Then computation cost. And we normally perform searching and sorting and merging in memory. That is the blocks which are available in the buffer. That is the memory. That is, what is the cost that is involved in performing in-memory searching, sorting and then merging. That is one cost component. The next one is memory usage cost. The number of memory buffers that are needed to perform the query execution. Then lastly, the communication cost. That is, if a query is submitted by some client which is connected to the server through some network, then cost of shipping the query to the database site and then shipping back the result to the place where the query is originated. This also is a significant component in computing the cost of execution of a query. So the query optimizer will use both the heuristic rules and then the estimations for the query execution to decide upon the more reasonably effective or efficient strategies for executing the queries. So this is how the optimization takes place in executing SQL queries by database management systems. So in this part, we discussed what is a query tree, what is a query graph, what is the significance of these things, and what is the difference between a query tree representation and query graph representation. We have also seen heuristics in query optimization, and we discussed about the cost components that are involved in estimating the cost of execution of a query, based on which a query optimizer can take a decision about more suitable strategy to execute a query. Thank you very much.